Hello everyone and welcome to our today's class. It is our second lesson on the topic reflection at curved surfaces. So as usual, let me comment by giving you the quote of the day, which states that spending the whole of today complaining about what happened yesterday won't make your tomorrow any better. So we'll discuss that quote at the end of our class today. So today we'll be looking at an experiment which is involving to determine the center of gravity of a concave mirror. So the apparatus that you require in this experiment are: one, you need a candle which will act as our source of light. Then you also need a cross wire which we will use as our object. Then you need some stands. Then of course you also need a concave mirror, of course, which is supported on a particular stand. So the procedure involved in this experiment is that, first of all, you support the white screen S with a hole having two cross wires O in line with the position of the mirror. So first of all, you arrange the apparatus as shown in this particular experiment. That is, you ensure that the concave mirror is at level with the holes, the hole that you've made on this particular stand, of course having a cross wire. Then so it has to be at the same level or at the same position with the candle, which is our source of light. So the procedure is that you support the white screen S. This is what we are calling our white screen. So you support the white screen S with a hole having two cross wires. So this is our hole having two cross wires which are acting as our objects, then in line with the pole of the mirror. So this cross wire, that is where you have made your hole, it has to be in line or parallel with your concave mirror. Then after that, you move the mirror carefully. So we are moving the stand having the mirror. So we move the concave mirror either closer or further. So you move the mirror carefully until a sharp image I is obtained near O. So you move this particular mirror, concave mirror, either closer to this particular object or the cross wire or further from the cross wire. So you move it, the mirror, either closer or further from the wire until a very sharp image is formed actually on S, that is near the object. So you move the mirror carefully until a sharp image I, this is what we are calling our sharp image I, is formed near O. Then O, in this case, remember O is representing our object. So O is the center of curvature of the mirror. So remember, our purpose was to determine the position of center of curvature of the mirror. So O, that is the position whereby the screen will be in such a way that after moving the concave mirror, actually a sharp image, a very sharp image is formed near O, that is on the same screen S. Then the point O is representing our position of center of curvature. Then while the distance MI, that is the distance from the mirror, that is to where the image is formed, this particular distance MI is representing the radius of curvature. Remember, we did say that the radius of curvature is the radius of the sphere for which the actually the image is formed. That is the distance from the screen, to where the image is formed. This is what we are calling the R, or the radius of curvature. So remember that if you already have R, then you can easily determine your focal length, or what you are calling F, because we did say that the focal length is always twice the radius of curvature. So if you have a radius of curvature of maybe around 10 centimeters, then it means your focal length will be 10 divided by 2, which will be equal to 5 centimeters. So if you are required to find, if you are asked to describe a simple experiment to determine the position of center of curvature of a concave mirror, first of all, the apparatus you need are a candle, then you need cross wires as your object, then of course you need a screen with a stand supporting it. Then we've said the procedure involved is that you support the white screen S. This is our white screen S. So you support the white screen S with a hole having two cross wires O. This is our hole having two cross wires O. You support it in line with the pole of the mirror. So this is our mirror. So you ensure that the hole, that is the cross wires, the hole having the cross wires and the mirror are at the same in line, or they are parallel to each other. Then after that, you move the mirror carefully until a sharp image eye is obtained near the O. So you move the concave mirror either closer or further away from the white screen until you will see a sharp image formed on this particular screen. So when that particular image is formed, then O, that is the position of the cross wire or the object, is said to be the position of center of curvature of that particular concave mirror. Then the distance MI, that is the distance from the concave mirror to where the image is formed. This particular distance will be equivalent to the radius of curvature, because if this is our center of curvature, then it means the distance from the center of curvature to the concave mirror. Remember the concave mirror, that's where we'll have the pole. So the distance from the pole to the center of curvature actually represents the radius of curvature. Then half of this distance will be equal to the focal length. Then after that, we also look at another experiment which is involving to estimate the focal length, that is a small f, of a concave mirror. So how do we determine the focal length of a concave mirror? So here the apparatus you need is just a concave mirror, which is we are denoting by M. Then of course a screen where your image will be formed. Then of course a window which is acting as our source or our object, that is rays coming from the sun or rays from infinity. So the procedure involved in this experiment is that, one, you move the white screen S in front of the concave mirror. So this is our white screen S. So you move either the white screen either closer to our concave mirror or further away from the concave mirror. So you just move the white screen S in front of the concave mirror until an inverted sharp image of the window frame is formed on it. So you just move the white screen either closer or further away from our concave mirror M until a sharp image of the window frame is formed on it. So when you realize that a sharp image of the window frame has been formed on it, then the distance MS, that is the distance from your screen, that is where the image is formed, and the distance from where your screen is formed actually measured from the concave mirror, that is, remember the concave mirror represents, that is where we'll have our pole. So the distance from the pole to the mirror, that distance will simply represent our focal length. Why? Because remember, for this case, these rays of light are actually emanating from the sun or any other relevant source of heat. So because the sun is further away from the earth, then these particular rays of light are reflecting, they are representing the rays from infinity. So remember, we did say that parallel rays which are from infinity and which are not parallel to the principal axis, they will always be formed at the focal plane. So the distance from the focal plane, and remember the focal plane always passes through the principal focus. So the distance from the principal focus, that is where we have the focal plane, to actually the pole where we have the mirror, that distance is the focal length. So remember, we did say that focal length is actually the distance from the pole to the principal focus. So these are parallel rays which are not parallel to the principal axis. So we did say that parallel rays not parallel to the principal axis, they will always be formed at the principal focus or the focal plane. So if this is where we are having our sharp window frame being formed, it means that window frame will be formed at the plane of the principal focus, or what we are calling the principal focus, actually the principal focus or the plane. So the position where we have our principal focus, that is where we have the focal plane. So the distance from the focal plane or the distance from the principal focus measured from the mirror, remember the mirror has the pole, so the distance from the pole to the focal plane or the principal focus is what we are calling the the focal length. So this is our focal length, that is the distance from M to actually S, because that is the distance from the pole, that is the pole will always be on the mirror, and the distance from the pole, that is to the principal focus. So this is what we are calling our F. So we have said that the procedure involved is that you just arrange the apparatus as shown here, then you move this particular white screen either closer or further away from the concave mirror until an inverted sharp image of the window frame is formed on it. So the distance ms, that is the distance from the principal focus, or where we have our concave mirror, that is to the focal plane, or where we have our principal focus, will be equivalent to the focal length of the mirror. So this is our focal length. So remember, you can also obtain the radius of curvature from the focal length, because we did say that the radius of curvature will always be twice the focal length. So if you have a focal length having of maybe 5 centimeters, then the radius of curvature will be twice that. That is 2 times 5, which of course will be equal to 10 centimeters. So that is how to obtain the focal length of a concave mirror, and also how to obtain the center of curvature of a concave mirror. So this relationship is also important because it will help us in some calculations later. So it is always important to remember that the radius of curvature will always be twice the focal length. Then we look at ray diagrams. We look at ray diagrams, which will involve simply formation of images. So images are located by use of ray diagrams. So any two rays, so ray diagrams, they are just diagrams showing the path of motion of the rays of light, that is from the object until they form the image. That is the path of the rays of light as they emerge from the object, then they hit the screen, then they converge or maybe diverge to form an image. So that is what we are calling a ray diagram. So a ray diagram is just a diagram showing the rays of light, how they emanate from the object until they are reflected from the screen, then until they form our image. So we are saying that actually diagrams, images are located by use of ray diagrams. So any two relevant rays, any two rays can be used to locate the image at their point of intersection, or where they appear to meet. That is the point of intersection for the case of concave mirrors, and where they appear to meet for the case of convex mirrors. So what are these rays that we use to locate the images? That is for ray diagrams. So the first ray that we use to locate our image is a ray through C. Remember, C in physics represents the center of curvature. So a ray through C is reflected along the same path for concave mirrors, so as it can be shown here. So a ray of light passing through the center of curvature, or C, will always be reflected along the same path. So you can see this was our incident ray, because the arrows will always emanate from the object. Then after hitting our concave mirror, it is reflected through the same path. So it is coming this way, that is before reflection. After hitting the mirror, the concave mirror, it is reflected through the same path. So our first ray is that a ray through C, that is a ray through the center of curvature, is reflected along the same path for concave mirrors. And a ray appearing to pass through C is reflected along the same path for convex mirrors. So this represents the case for the convex mirrors. So remember, we did say that convex mirrors are also called diverging mirrors, whereas concave mirrors, we also said that they are called converging mirrors. So if you have a ray of light appearing to pass through C, so we are saying appearing because this ray of light, the center of curvature and even the principal focus for the case of convex mirrors are always located behind the mirror. But for the case of concave mirrors, C and F are always located in front of the mirror. That is, C represents the center of curvature, whereas F represents the principal focus. So a ray of light, a ray appearing to pass through C is also reflected along the same path for the case of convex mirrors. So a ray of light which is coming from a given distant object, when it hits the convex mirror, it is actually reflected along the same path. So it was coming downwards, after hitting the mirror, then it is reflected along the same path. So it appears to be reflected along the same path because remember, the rays of light behind the mirror, we usually use dotted lines. We call them virtual rays. So we will differentiate later. We'll look at the difference between a virtual and a real ray. For example, for this case, after reflection, we are representing it by full line. So this one represent the real rays, and real rays in most cases they will form real images, whereas for this case these are behind the mirror. So these are what we are calling the virtual rays. So virtual rays in physics, we always represent them by dotted lines, whereas real rays in physics, we always represent them by full lines. Then our second ray is that a ray close and parallel to the principal axis is reflected through F. That is for the case of concave mirrors. So as you can see here, we have our concave mirror, a ray of light which is a ray of light close and parallel to the principal axis. So remember, this black line is the one representing our principal axis, because we know that principal axis always connect the center of curvature to the pole of the mirror. So if you have a ray of light which is close, as you can see, this ray of light is actually very close to the principal axis. So a ray of light which is close and parallel, remember, when two lines are parallel, it means they can never intersect each other. So this line which is incident and the principal axis, they actually parallel to each other because they can never intersect each other. So if you have a ray of light, a ray which is close and parallel to the principal axis is always reflected through the principal focus. That is for the case of concave mirror. So as you can see here, this array of light which is very close, which is close and parallel to the principal axis, then after hitting the concave mirror, it is always reflected through F. So as you can see here, it is passing through F. So remember, F in this case is actually the principal focus. So if you have a ray of light which is close and parallel to the principal axis, is reflected through F. That is for the case of concave mirrors. So do not confuse this with the parallel rays which are not parallel to the principal axis. So remember, if you have two parallel rays which are not parallel to the principal axis, they will always be reflected at the focal plane. So focal plane can be any distance along this line. But if you have rays which are close and parallel to the principal axis, they will always be reflected through F. That is for the case of concave mirrors. And if you have the same rays, a ray close and parallel to the principal axis is reflected in such a way that it appears to emerge or originate from the principal focus, which is F. That is for the case of convex mirrors. So for convex mirrors, if you have a ray of light which is close and parallel to the principal axis, remember this is our principal axis. So as you can see, this incident ray is actually very close and parallel to the principal axis. So if you have a ray of light which is close and parallel to the principal axis, for the case of convex mirrors, it will be reflected in such a way that it appears to emerge from F. So as you can see, this ray, it is appearing in such a way that you can actually imagine, imagine that it is originating from F. So it is reflected in such a way that it appears to emerge or originate from F. So it appears as if this ray is originating or emanating from F. So it moves from F actually upward. So those are the two rays. Then we look at our third ray. So we have a ray through F is reflected parallel to the principal axis. That is for the case of concave mirrors. So remember, the principle of reversibility of light stated that the path of light rays are reversible. So remember, we just looked at a ray of light which is parallel, which is close and parallel to the principal axis, and that ray was being reflected through F. Now if we have another ray now which is passing through F, it will now be reflected close and parallel to the principal axis. So we are just reversing the path of the light ray. So according to the principle of reversibility of light, which said that the path of light rays are reversible, that is where we obtain this ray. So we have, if you have a ray which is passing through the principal focus, it is reflected parallel to the principal axis. That is for the case of concave mirror. So as we can see here, we have a ray of light which is emanating from the object, then which is passing through F. After hitting the concave mirror, it is reflected parallel to the principal axis. So this is our principal axis. So if you look at this, principal axis is actually parallel to this reflected ray. So a ray of light through F is reflected parallel to the principal axis for the case of concave mirrors. Now for the case of convex mirrors, a ray appearing to be directed to F is reflected parallel to the principal axis. That is for the case of convex mirrors. So as you can see, this ray of light, it is appearing to be directed towards F. Appearing because F is behind the mirror, so we are just imagining that F is here. So this F is imaginary because you cannot see it. It is virtual. That's why you are seeing using the term appearing to be. So it is not real, it is virtual. It is just like for the case where when you look at yourself through a mirror, actually your image appears to be behind the mirror. But if you go behind the mirror, you cannot touch that image, meaning it is virtual or it is imaginary. So we are saying that a ray appearing to be directed through F, that is for the case of convex mirrors, it will be reflected parallel to the principal axis. So this ray is appearing to be directed towards F, then upon hitting the convex mirror, it is reflected parallel to the principal axis. Then 4, if you have a ray at an angle to the principal axis and incident to the pole, it is reflected in such a way that the angle of incidence will be equal to the angle of reflection. So this ray of light or law is coming from the laws of reflection, which stated that the angle of incident must be equal to the angles of reflection. So if you have a ray of light at an angle to the principal axis, so at an angle, like for this case, I have this ray of light which is hitting my mirror, that is the concave mirror, at an angle. For example, if my angle is I, that is the angle from the principal axis to the ray. This is what I'm calling I. I is representing the angle of incidence. So a ray of light at an angle to the principal axis and incident to the pole. This is the pole is supposed to be somewhere here. So if this ray is incident means that is where it is coming to hit. So if you have a ray at an angle to the principal axis and incident to the pole, it is reflected in such a way that the angle of incident, that is I, will always be equal to the angle of reflection. So this angle of incidence will always be equal to the angle of reflection, that is after hitting the mirror. So for the case of convex mirrors, it is still the same case. So I have a ray of light which is incident on the principal on the pole, which is incident on the pole, and it is also it is incident at an angle on the principal axis. So it is forming at an angle I with the principal axis, then it is incident on the pole, then upon reflection it is reflected in such a way that the angle of incidence will be equal to the angle of reflection. So here you can see I, which is the angle of incidence, must be equal to the angle of reflection. Also here the angle of incident must be equal to the angle of reflection. So remember, we did say that the angle of incident is the angle formed between the incident ray and the principal axis for this case. Then the angle of reflection represents the angle formed by the principal axis and the incident ray. So this is the incident ray, this is the reflected ray, then this is the incident ray. So the angle between the incident ray and the principal axis is what we are calling the angle of incidence. Then the angle between the reflected ray and the principal axis is what we are calling the angle of reflection. Then we look at image formation and their characteristics. So first of all, we start with locating image formed by a concave mirror. So we start with our first position, whereby we are placing our object at infinity. So remember, infinity means a distance far away from our mirror. So like for this case, we can take rays from the sun, because the sun is further away from the earth. So the rays of light which are emanating from the sun, we are referring to them as rays from infinity. Those are rays from infinity. So remember, we did say that parallel rays, which are not parallel to the principal axis, they will always be reflected at the focal plane. So here, if you have rays of light from distant object, that is an object which is at a greater distance or far away from the actually concave mirror, then such rays of light, upon reflection on our concave mirror, they will be reflected at the focal plane. This is our focal plane. So remember, we did say that so for this case, the rays will always meet at the focal plane. So meaning our object will be at the focal plane or at F. So in this case, rays of light which are parallel rays, not parallel to the principal axis, they will always converge at the focal plane. That is for the case of concave mirrors. So in terms of diagrams, ray diagrams, this is how we represent our concave mirror. So as you can see, the reflecting surface is inward while the outer surface is shaded, which is or silvered or highly polished. So the characteristics of the image formed is that, one, the image is formed at F. So as you can see here, our image will be formed at F. Then we are imagining that the object was somewhere here, because the rays of light have to emanate from the object. So if the rays of light are emanating from somewhere here, it means the head of our object was here, therefore the object was upright. It was upright. But the image is facing downward, therefore the characteristic of the image formed is that, one, it is formed at F, that is where it is located. So the image is formed at the principal focus. Then the image formed is real. Real means it can be formed on the screen. Then the image formed is also inverted. Inverted means it is upside down. So if our object was facing upward, then the image is facing downwards. It means our image is inverted. That is relative to the object. Then another thing is that the image formed is diminished. Diminished means it is reduced in size. So because we are imagining if our object was from here up to where the rays emanated, then the object must have been very large. Therefore the image is smaller. Therefore we say that the image is diminished. So the characteristic of the image formed is that, one, the image is formed at F, that is at the principal focus. Then the image formed is real, that is it's formed on the screen. Then the image formed is inverted. Then lastly the image formed is diminished or smaller than the object. Then if we place the object beyond C, that is at a distance far away from our, remember C in this case is representing the center of curvature. So if an object is placed beyond C, then the rays that we'll use to locate is that we use any two relevant rays. For this case we are using a ray of light which is close and parallel to the principal axis. We said it will always be reflected through F. So a ray of light close and parallel to the principal axis is reflected through F. Then a ray of light through C, that is a ray of light through the center of curvature, is reflected through the same path. So the ray of light is emanating from the object, then it passes through C, it hits our concave mirror, it is reflected through the same path. That is, it is coming downwards. After hitting the mirror, it is reflected through the same path. So the point of intersection of those two rays represents at the head of our image. So the image will be formed here. So as you can see here, the image, if you compare the object and the image is actually reduced in size, or we said it is diminished. So the characteristics of the image formed is that, one, the image is formed between C and F. That is between the center of curvature and the principal focus. So the image is between C and F. Then two is that the image formed is real. That is, it is represented by full lines, or it can be formed on the screen. Then three is that the image formed is also inverted. As you can see, the object was facing upwards while the image is facing downwards. So in this case, we say that the image is inverted. Then lastly, the image is diminished. Diminished means it is reduced in size. So the object was large, the image is actually smaller as you compare to the object. So we say that the image is diminished or reduced in size. Next, we look at when we place the object at C. That is when the object is placed at the center of curvature. Then we use any two relevant rays that we've discussed. So like in this case, we are using that a ray of light which is close and parallel to the principal axis. So you can see this ray of light emanating from the object. Remember that rays of light will always originate from the object towards the image. So a ray of light which is, remember we said that you can use any two relevant rays. It is not a must that you use the ones that I'm using. So you can just pick any two, then the object will exactly, the image formed will exactly be at the same position. So a ray of light which is close and parallel to the principal axis, after hitting the concave mirror, it is reflected through F. Then a ray of light through F, is reflected parallel to the principal axis. So where are these two rays of light? That is this ray, the first ray of light which was close and parallel to the principal axis, then it is being reflected through F. Then we also have a ray of light through F being reflected parallel to the principal axis. Then those rays of light, where they intersect, it represents the head of our image. So the image is here. So this is our image. So as you can see here, the image is formed at C, that is the image is formed at the center of curvature. Then 2, the image is real, that is it is formed by real intersection of the rays of light. Then also the image is inverted. As you can see, the object was facing upwards, the image is facing downwards, so the image is inverted. And lastly, the image is of same size as the object. That is, when you compare the length or the size of the object is the same as the size of the image, so the image is of the same size as the object. Then if we place the object between C and F, that is when the object is placed between the center of curvature and the principal focus, then here we also use 2 rays of light close and parallel to the principal axis will always be reflected through F, so that's our first ray of light. Then a ray of light through C is reflected through the same path. So the ray of light is emanated from the object. After hitting our mirror, it is reflected through the same path. So the point of intersection of those 2 rays represents the head of our image. So as you can see, the image is formed here. So characteristics of the image formed is that the image is formed beyond C. The image is formed beyond C. That is, our image is further away from C. Then the image is real. Why? Because it is represented by full lines and it is on the same side as our object. Then the image is inverted. That is, the object was facing upwards, whereas our image is facing downwards. So in this case, we say that the image is inverted. Then the image is magnified. That is, the object was smaller while the image is larger. So to say that it is magnified, it simply means that the image is larger than our object. So those are the characteristics of the image formed. So in an exam, this is the diagram that is mostly tested. Why? Because the characteristics of the image are slightly different from those of other positions. So students should be very keen when handling such. So remember, for the case of concave mirrors, whenever an image is formed on the same size or on the same side as the object, then that particular image will always be real. It will always be real. Then we look at when we place the object at F. That is, if we place the object at the principal focus, now what happens? Rays of light close and parallel to the principal axis are reflected through F. Then a ray of light through C is reflected through the same path. That is, from the object, it hits our concave mirror, then it is reflected through the same path. So in this case, you realize that the rays, after emerging, they are parallel to each other, meaning they will not meet any place nearer. So in this case, we say that the image will be formed at infinity. Infinity is further away. So you continue drawing these lines, they will meet at a further distance. So we say that the image will be formed at infinity or further away. So the characteristic of the image formed is that the image will be formed at infinity, or we can also conclude that the image will be formed further away from C. Then if we place the object between F and P, that is, if the object is placed between F is the principal focus and C is the center of curvature, then in this case we use, of course, any 2 relevant rays. So rays of light close and parallel to the principal axis is reflected through F. Then a ray of light through C is reflected through the same path. So in this case, you realize that the rays of light in this case appear to be diverging. So in this case, the rays of light will never meet. So we extend them on the other side. So the image is formed behind the screen. So for the case of concave mirrors, whenever an image is formed behind the screen, then the characteristic of such an image is that it will always be virtual. Virtual means it is not formed by real intersection of the rays. So the image is formed behind the screen and it is also magnified. So the characteristic of the image formed is that 1, the image is formed behind the mirror. 2, the image is virtual. Then 3, the image is upright. As you can see, upright means it is facing upwards. That is, it is exactly the same as the object. If the object was facing upwards, the image is also facing upward, then we say they are upright. But if they are facing in opposite direction, then we say they are inverted. Then the image is also magnified. Magnified means the image is larger than the object. That is, you compare the size of the image, it's far much larger than the size of the object. Then we look at the difference between a real and a virtual image. The difference between a real and a virtual image. So a real image, this refers to images that are formed by actual intersection of the rays, or these are images that are formed on the screen while virtual images, they are not formed on the screen, or virtual images are not formed by the actual intersection of the rays. Then lastly, we look at concave mirrors. That is, for concave, for all positions of the object, the concave mirrors form images of the following characteristic. So like we just look at one position, of course here a ray of light parallel, close and parallel to the principal axis, a ray of light close and parallel to the principal axis appears to be emerging. It is reflected in such a way that it appears to be emerging from F. Then a ray of light, of course, appearing to be passing through C is reflected through the same path. So if you use those two rays, we can actually locate our image. So the image is simply located here. So for all positions of concave mirrors, for all position of objects, concave mirrors form images of the following characteristics. 1, images that are always upright. 2, images that are diminished. So upright because it is facing on the same side as our object. Then the image is diminished. Diminished means reduced in size. So as you can see, the object is large while the image is smaller. Then the image is virtual. Why? Because it is formed behind the screen. So virtual images are always represented by dotted lines as seen here. Then the image is always formed between P and F. That is between the principal focus and the principal focus and of course the pole. So we've come to the end of our class today, but we need to discuss the quote of the day. So the quote of the day stated that spending the whole of today complaining about what happened yesterday won't make your tomorrow any better. So what does this particular quote mean? So the quote is warning us against shunning away from taking full responsibility by making excuses and complaints. Remember this: before you complain about your job, take a minute to first think of those who are jobless. And before you complain about the low quality of infrastructure in your school, take a minute to first think of those who are at home because they lack school fees to access education from a school such as yours. Then, before you complain about your parents, take a minute to first think of those who are total orphans. So, we think that our problems can be solved by 1, making excuses, 2, complaining, 3, watching movies, 4, taking alcohol, 5, smoking, or 6, by remaining silent. So the truth is, those are just ways of suppressing and postponing our problems. Instead, we need to take full responsibility and address our problems instead of running or shunning away from them. And lastly, remember this: great people wear 2 things on their face. 1, a smile to laugh at their problems as they solve them, and 2, silence to avoid more problems. And lastly, about 10% of the people in the world are problem solvers, while 90% of the people in the world are problem creators. So I challenge you to be among the 10% who are the problem solvers. This is Kind Tuition Academy. Kindly hit that subscription button on YouTube. Thank you.